Nào nhau rồi vì người này buồn đã rồi ngày giây phút trôi xa người tình đã.
Okay, today we'll be talking about bipolar transistor for DC bias. Okay, first thing you can see they given to you a few symbol for NPN transistor. That one here, NPN. Another one will be PNP. You get only two. Okay, how do we recognize NPN or PNP? You see arrow coming out. That will be NPN. This one opposite coming in for PNP. Okay, and basically they get three terminals. One will be a base, okay, and another one will be a collector, and this is the emitter, okay, and same thing. You get an emitter here for PNP, collector, and the base. You can see the difference between the current flowing. NPN, the current flow into, okay, transistor. IC means collector current flow into it. However, emitter will be leaving, and the formula will be applied to the transistor. Okay, first thing you can see they say IE emitter current will be equal to IC plus IB. Okay, we don't care about that one. Okay, IC almost like IE. Okay, or IB is too small compared to IC. That doesn't matter. However, the one we need to know is the beta. Beta will be equal the ratio between the collector current and the base current. Okay, so now when you're looking into PNP, then the current IB leaving, okay, IC will be leaving, IE will be coming in, okay. This is a very, very basically, when you're looking into the symbol, you're able to recognize, okay, is it a NPN or PNP? Okay, later on telling you a little about physical, okay, of NPN and PNP transistor. Okay, general formula IE equal IC plus IB. Okay, and the beta equal ratio between IC divide IB. Beta means the amplifier gain. Okay, and also you can get the definition alpha. We don't care about that thing. Okay. Now, if you see that they show you physical for NPN here, basically they get two different, one N side and the other one P side. That only telling you they get two diode. PN, that's a diode. Okay, so P here and here, one diode, P here and here, another diode. And basically the P and P, they will be opposite. Okay, so basically they combine two diodes. Then you get a transistor. Okay, and this again showing you which one is NPN or PNP. That's the only thing you need to know. You don't care about physical. Okay, now this is the transistor when you're working on the lab. Okay, NPN and PNP. Okay, and if you say NPN, this is the base. You get a one diode from the base to the collector, and another diode from the base to the emitter. And again, P and P opposite. Okay, you get one diode from collector to the base, and one diode from emitter to the base. Okay, so basically you understand either NPN, PNP, they just combine two diodes. We already done for the diode. Okay, now if you're looking into this circuitry here, okay, you get the VBB, power supply, okay, and they get the current IB, okay, go to the base, and also the current IC coming out from VCC. They need two power supply, okay, and this is the current IE. Same thing for this PNP, they need also two power supply. Only thing is, power will be different polarity. This is the negative here, positive here, and the current IB going out. Okay, and this is the power supply VCC, negative, positive, and the current leaving. Okay, and IE coming in. I hope that will be make it more clear for everyone. Now, this is a NPN. Okay. Basically, you get a one power supply VBB, another one VCC. Okay. You get RB, you get RC here. Now, you can see you get a current flow here coming in. Only thing is, you know, this is a diode. And the voltage from the base to the emitter will be 0.7 volt. Okay. And this is a formula, okay, will be helping you to do calculation. However, just for general understanding, the thing is if you want to know what the voltage, you can run the simulation. So that's why they don't have to go too detailed in order to do calculation. Okay. Anything you want, you can using the MSIM7 simulation or PSPI simulation. Okay. You run it, they're telling you every current, every voltage. Okay. We don't have to do the calculation. However, when you're looking into the schematic, you know NPN or PNP. Okay. And by the way, I can tell you, if I draw the, the loop going, okay, the first thing when you hit into VBB negative, then you using minus VBB, okay? Then you go to the RB, the current in RB here, you know that current will be IB. So you adding IB time RB. When you hitting into the V voltage from a base to admitter, that's a 0.7. Plus side, negative side. So that's why you plus 0.7. Okay, equal 0. Okay. From this formula, you can calculate the current IB. If you want, you just using the formula. IB equal VBB minus VBE divide RB. Okay. And also, you get the VCC, RC, the current IC. Okay. This is the collector. This is the base. And this is the admitter. Okay. Now, if I want to calculate the VC, how can I calculate it? What VC you think?
First, you know the number beta or beta.
VC, that means voltage from collector to the ground. Okay.
Right. So you're gonna do VCC minus IC times RC, where IC is beta times IB. So that's your solution right there.
Yeah. Okay. VC, that means this is the VCC. So we need to know how much the voltage drop across the RC. That's why you can get VC. So basically, VC will be equal VCC minus IC times RC. Okay. That is how can we do calculation VC. Okay. In this schematic here, what we VB equal? Now, again, if we said I want measure VB. That means the DMM high side connect to the base, and the low side must be connected to the ground. So if you're looking into the schematic, what VB in this situation equal what?
It's the diode potential 0.7. If ground is on E, we don't
Yeah,
have a
down
ground
here.
here in our picture.
All
Okay.
right. Yeah, 0.7 volt. In this case, if I want to calculate the VCE, how?
We have to do to subtract VE from VC. So VC minus VE,
Perfect.
yeah. But in this case, VE is 0, so it's just VC. Okay.
Yeah, that right now we're just talking about if you're looking in schematic, we want to do calculation. Okay. Then you know how to do. Same thing. If we want to measure the VCE, that means high side meter connect to the collector and the low side connect to the meter. Okay. Everything we already showed you in here. Okay. So try to read it again.
Hey, Mr. Pham,
Yes, sir.
is that the VBE? That's 0.7, right?
VBE, right?
Yeah, it's 0.7.
Exactly. In this case,
Yeah. So why did you write VB equals 0.7?
Because
that
he's
means
looking
talking
for a
about
potential base
they're talking
relevant to
about
the
the
ground.
You're both talking at the same time. Go ahead.
same thing. Now they're talking about from the base to the meter.
Oh, base to the emitter.
In this case, however, later on, VBE is not 0.7. If you get a resistor here,
Right, right.
that apply only for this schematic.
Okay.
Now, basically, they said they want IB, IC, IE, VBE, VB, VCE, VC, VCE. In the circuit cell, the transistor has a beta. That means the voltage gate equal 100. That will be given by manufacturer. You cannot make it up. Okay? And also they given you VBE 0.7 volt. That for silicon diode. So quickly we can see they want VBE, VBE. Okay? Then you know VBE just a voltage across the diode. They will be 0.7 volt. Here. And now they want to calculate the IB. Okay? So if you want to do calculation, you can go into here. Here. Using this formula, IB equal IE divide 1 plus beta. Okay, IB equal IE IE divide 1 plus beta. We already know IE equal IB plus IC. However, they don't want to using that formula. Okay. If you want to calculate the IB, you better using the IE divide 1 plus beta. Okay.
So in this one here, the be- based on your figures, I see 43 milliamps over IB 0.43 milliamps. That comes out to 100.
However,
So what is the 150 for?
what do you mean 54?
No. I'm asking you, what is at the very top in the blue writing where you highlighted in yellow? You got beta equal 150, then you got beta equal 100.
Let's see. Transistor had a
In
beta.
the in the blue
Oh,
writing,
okay. I see what you say. Okay, thank you. That
and,
will
and
be,
when you do the calculations with IC divided by IB, 43 milliamps divided by 0.43 milliamps, that comes out to 100. So that's why I was asking you.
yeah,
What,
thank you. That's a typo.
yeah.
Thank you. Okay, now number 1A 0.7. Can you telling me how can you get IB? Remember,
You showed it earlier, right? You know, the VBB minus VBE divided by RB.
in here, right? VBB minus VBE divide RB. Okay. Minus VBE divide that is how you get 0.43 milliamp. Okay. I see you using the formula beta time IB. Okay. IE. Okay. Now again, I want to make sure you understand. You get IE, IB, I see. But we don't want to using this formula. Okay. Remember, we want you to using the other one. One blood beta time IB. Okay. And now they want VB. Easy, right? You already know IB. So, law. Okay. IB time RB. VE, easy to recognize. The thing that they connect to the route. VC, again, they will be equal VCC minus IC time RC.
Just one comment on VB. This is not 100% correct what you wrote there. That's the voltage drop on that resistor, but not the VB. So that is the part of it. So you can say VBB minus that would be correct.
Okay.
Right.
You good. Okay. Let's see. VC, that means
Hey, Mr. Fan, before you do VC, you got to change the letter E, don't you? Based on what he just said, or not?
No, I was talking about VB, that it is this formula that we have written is just partially correct. You are missing some parts.
Yeah, so then
V is correct.
it's correct like that?
VC equal VCC minus that is the formula to calculate it. Last one, VCE. VC. Normally, that is just a very basic calculation. Normally, they're not using that type of connection. Why? The thing is, in this time, they need two power supply. 1 5 volt, 110. That's what they don't want. Got more money. Okay? However, we just try to bring it up for you so you get an idea about how do we calculate on of the current IB, ICIE, VB, VC, VE, or VCE. If you get a question, okay, go ahead and ask it.
I have a
Now,
quick question. So does a transistor circuit always require two power sources?
no, they're not using two power.
Okay.
We'll see later.
Okay.
Okay? Yeah, the thing is, two power supply cost more money. At it. Now, region of operation. So basically, the transistor, okay, they can using first one cut off region. That using in switching application. Okay, that means turn it on or turn it off. Okay, so either they connect to high or they connect to low. That's the normal. That transistor must be in cutoff. Okay. Second thing, active region. They want to using the transistor to design amplifier. Okay. Then the transistor must be inactive. Okay. And the last one, saturation. Same thing, like cutoff used in switching application. Okay. Last part, break it down. Cannot will be destroy the transistor. Okay. So we cannot using that. So make sure again. Okay. Transistor can be cut off, or they can be active, or they can be a saturation. Depend on the application. You want to design an amplifier, then the transistor must be in active region. Okay? Or you want just a switching, turn on, turn off, they have to be either cut off and a saturation. Okay. Now what they say in here. Okay. Cut off diode from B to emitter E off. Okay. In the cutoff, then the diode from the base to the emitter will be off. Active diode from the base to the emitter must be on, and diode from the base to collector must be off. Saturation, both diodes are on. Okay, and VCE equal 0. Okay, so basically on that one, they bring it up to you in generally how we can using the transistor. Okay, you want to use transistor for cutoff or for active or for saturation. Okay, and for each one, they will be applied to whatever you want to do. Now, example. For the transistor circuit shown, what is VCE? That means voltage. When V in equal 0.
If Vn is 0, there's no current flowing. So
Okay. Go ahead.
VC is 10, VE is 0. So VCE will be 0.
Huh. Okay. Now,
10.
VCE. That
No,
means
because you don't have collector current. That means this voltage 10 volts goes all the way down to the collector. It passes right through the RC. So the answer is 10 volts.
that means you said the answer for VCE 10 volt.
Yes.
Perfect.
Yeah, Branko's got it.
Yeah. I try to explain to everyone. Okay. First thing, you see 0 volt here. So this diode here will be off anyway, correct? That means diode from base to emitter will be off. Off means they will be open. Okay? When they open, then no current can be flow. IB, IC, IE will be 0. Transistor open. Okay, now in here, 10 volt. When no current flow, what voltage drop here? If you want the VRC, that means IC times RC. However, no current, IC 0. So no voltage drop in here. That will be telling you, you get 10 volt here, then VC must be 10 volt. The thing is they not drop any voltage. Okay. So VCE means from collector to the ground. That's what they will be equal 10 volt. Okay. In solution here, we already tried to explain to you. Okay. Try to read it. What minimum value of IB is required to saturate this transistor if the beta equal to 100. Okay, say what they're telling you. Since transistor saturate if VCE equal 0. Okay, let's see. You see that here, saturation, VCE equal 0. Okay, that will be telling you IC saturate equal VCC divide RC. You get 10 milliamp. Okay, therefore IB equal IC saturate divide beta, you get 10 milliamp. Divide 200, you get 50 microamp. Okay, that means they are asking for minimum value of IB. Calculate the maximum value of RB when V in equal 5 volt. Okay, so now you get the 5 volt here. Okay, they want to know maximum value RB. See how they do. When the transistor is on voltage across RB, then VRB equal V in minus VBE. You get 4.3. Okay, then RB maximum will be equal VRB divide IB minimum. That given you 86 kilo ohm. Basically, if you get the time, you can read it through it, okay? Now, this is another thing.
That might be maybe the minimum RB, not the maximum.
Which one?
The 86 kilo ohm. So I think that's the smallest we can put that.
86
Because
kilo ohm. That means they're telling you maximum value.
Yeah, but is it maximum or is it minimum? If I put smaller, I'll get more current. That's a problem, right?
Let's see. When the transistor is on voltage across RB, okay, V in divide VBE. That's correct. Okay. Then what we want to telling you is they say IB will be minimum. Okay.
Right. So that's the smallest you can put, because if you put smaller than that, you're gonna get the saturation problems. It's gonna be distorted.
Right. That make it saturated.
Right.
So that's why in here they calculated 50 microamp.
Right.
Okay.
I'm just saying that even if you put bigger than the maximum, it's not gonna be fine. Okay, doesn't matter. It just the word is wrong, like
Yeah.
like that.
Now that one. You can see that it stands for IE. Okay. IE in milliamp. 2 milliamp for 6, 8, 10, and so on. And another one here stand for VCE in volt. Okay, now what is it here? What is it? Stand for what? You see?
Oh, you mean like 40 microamps
Yeah,
for
20,
IB?
40, 60, 80, 100 micro.
Yeah, but that's for IB.
That will be stand for IB. Okay, if you get right here, this one here, you can say what IB equal. They will be 60 microamp. If you want the VCE, you going down here. They will be 10 volt. If you want the current IC, you go to the left. That's why you can get current. Okay.
And that's the ideal optimum area where you want to operate the transistor.
Right. So that will be helping the people. If you want to design the amplifier, okay, so basically you have to select, okay, resistor, okay, and make sure transistor not cut off or transistor not saturated. They have to be active. That we already talking here. Okay. If you want design transistor for amplifier, and they have to be inactive. They cannot be in cutoff. They cannot be in saturation. Okay. So you can see in here, we pick a point we call Q point. So at the Q point, you know what the current IB. Okay, you know what the voltage VCE and also the current IC. So you get the current IC, IB, and VCE. That will be helping you to select the resistor. Okay, to connect it to get the current you want. And in here, they show you three area here. This is the next area right here. That's what they call saturation. Saturation. Okay. If you get the point right here, the point right at this point, they be saturated. Okay. And another one will be cut off. That means if you get any point down here, okay, transistor will be cut off. So basically, this will be telling you, okay, if you designer, you want transistor to be switching on and off, then they can be in saturation or cut off. However, if you want to amplify your voice, then they have to be in active, okay? And they already telling you here, this is active here, okay? So normally, you want to design the amplifier, you have to get the Q point. For example, here, you get the current IB, IC, VCE, and now you can select the resistor to make that current. However, they're telling you, they don't want you to pick it up the point in here. Why? The reason is when temperature going up, this Q point can be moving. Otherwise, they can be moved to the saturation. That's what you don't want. Okay? Or any point close to here. Okay? They can be go to the cutoff. That cannot be happen. So that's why the Q point normally they pick it up in the middle here. They can moving, okay, up or down. That doesn't matter. Okay? And also they can telling you NPN or PNP transistor controlled by current control. NPN or PNP. Current controller device. That means basically they control by the current. Okay. Later on, when you're learning about the FET, that's another transistor. They will be controlled by the voltage. That's what they call a DC load line. Okay. In order to draw this line, first thing, point A, right here, at saturation, I saturate equal VCC divided to RC. Okay. In this case, okay, 10 volt divide 1K, you get 10 milliamp. Okay. I saturation. So you get the IC, I saturate, okay, equal 10 milliamp. You get 1 point. And now you get another point. Point B, at the cutoff, we already know at the cutoff VCE equal VCC. Okay, so you get the VCC 10 volt. So that's why this will be a 10 volt here. Okay, and you get the saturation current. You get another point here. You draw the line. That line they call a DC load line. So now you want to design. You say, okay, I want a Q point here. And that will be telling you current IB of the Q point going down VCE. Go to the left, you get IC. Okay, they must be on the load line. You don't want that, they have to be here. Okay, or here, anywhere. However, we want amplify supposed to be in the middle. Okay, so if I given you the circuit, you're able to draw the DC load line. Okay, that the DC load line get the current IC, and another one point will be VCC. Hopefully everyone know how to draw that DC load line. Now we see here. Let's see, cut off, open switch. If you apply a 0 voltage, transistor will be open. No current flow. So they like the switch, they open between collector and the ammeter. Okay. Next one will be amplifier. Okay. This is a saturation. Let's see, like a closed switch. Okay. That means they don't have any gain, anything. They just try to connect collector to ammeter. Okay. Or they could be open collector to the ammeter. Okay. That means either cut off or saturation. Okay. Okay, this one, example, you guys can look into that. We don't want to emphasize on the not practical circuitry. Okay. This is the solution for you guys. Now, example number 4. What they want? They want to determine the Q point for the circuit cell. Given beta 200, that means you need to calculate IB, IC, IE, VCE. Okay. So we already talking about do calculation before. Okay. And now they say and draw the DC load line. Okay. DC load line, you know that IC will be IC saturation. If you don't know how to calculate it, they're already telling you here. IC saturation equal VCC divide RC. Okay. And also you need that point. They equal VCC. Okay. And you draw the line. That means we go a DC load line. Okay. They get a solution for you. If you get a time, you can read for your understanding. Okay. This one also, we already doing calculation here. You can looking into that. The thing is we never have to do calculation. If you go to the city column, then you need to do. The thing is they only based on theory. Okay. Even this is not, supposed to be keep applied. Why? If you want any voltage, any current, you get a simulation. Okay? Why you need to do that calculation? Okay? Another admitter feedback bias. Okay? That means another circuitry. Okay? Calculation for DC current and voltage. What they say here, better than B bias. That means better than this one, B bias. Q point still move. So that's why not using, okay? But we just show up to you here, okay? When you see this circuitry, you know what is it. If you want to know the value, they have to given you VCC, RB, RC, RE. You go to the simulation, okay? You can get bias, the least predictable, Q point move with temperature not practical. That one you never see. Collector feedback bias, better than 8 meter feedback. Q point still move, limited application. The thing is when you design the amplifier, you have to get the Q point, and you don't want that Q point move for any reason. Okay? Two power supply, admitter bias. Now they're using two. One positive, one negative. Very stable. However, require two power supply. That's what they don't want. Okay, this is the calculation. If you get the time, you can go through that, get everything already calculated for you. And if you get any question, we'll be helping you. Now, this is the one. Only the one will be using on the top. That means we call a voltage divider bias. So up to this point, only thing I want you to working on this divider. Okay, bias. First thing, you can see the difference here. Is the adding R1, R2 resistor. You know resistor 5 cents, X1. So basically you get 10 cents and then you make it working. Instead you have to using two power supply. Power supply cost more, for sure. Okay? So make sure you have to get along with this voltage divider we're using all the time. Okay? First thing, they want to calculate the VBB here. you get a VCC. Okay, you get R1, R2. You can calculate the VBB using the voltage divider law. So VBB equal VCC times R2 divide R1 plus R2. Make sure if you get a question anything, just bring it up. Okay. Which one will be really need for you guys? So we want to emphasize. Okay. If you want to calculate the VBB, you're using voltage divider law. Okay. Now VE right here. VE equal VBB minus 0.7. You understand in here, positive, negative. That are for the diode. Okay. This is the base. This is the ammeter. Okay. So if you want to calculate the VE, you take VBB minus 0.7, you get VE. Okay. If you get a VE, easy for you to calculate the IE. Okay. IE equal VE divide RE. Okay. Right here. And now, if you want to calculate the IB again, we want you to using this formula. IE divide beta plus 1. R1 and R2 form a voltage divider. That's what we're talking about, divider law. Okay? And you want to calculate the IC, beta times IB. VRC, okay, equal IC times RC. And VC equal VCC minus IC RC. That's the all of the formula for this circuitry. You get any question, anything more working, you can get along with that. Okay? They will be using all the time. Voltage divider DC bias. Okay? They already telling you right here. That's what we're talking about. Voltage divider. If IB is not small enough to neglect compare to IQ, therefore, more detailed calculation needed. R in base. Okay, that means at the base, okay, they get a resistance. Okay, now, if I given you a meter, I want to measure RB. RB means resistance from the base to the ground. So you connect high side to the base and low side to the ground. That will be measured the resistance from the base to the ground. Okay. In here, they already telling you RB, RBB, the bay, divide IB, where R in bay, that is the resistance from VBB to the ground. Okay, VBB bay, okay, equal VBE plus IE times RE. That means VBB from here to the ground, okay, they will be equal 0.7 here, right? And also the voltage drop across the resistor, okay? So that's why they try to give you that thing. However, you can read that. We never care about that thing, okay? The thing is, you have to understand R in RB. That means resistance from the base to the ground. Okay? Basically, that one they given to you. The formula here. I in base equal VBB divide IB. Same thing, beta times IB times RE divide IB. This is the final formula. You take beta times RE, you can get I in base. Okay? This is the example. Now, what I want you to do calculation and telling me the answer. Go ahead and do it. The thing is this type of circuitry we're using all the time. So go ahead and do it. Whoever get the answer, let me know. I already given you all of the formula. Follow that and try to get along with the circuitry. Who got the VBB, let me know.
VBB should be 3.59 volts.
3.59. That's the one answer. Who else get the same? You have to do your calculation.
Yeah, I got that.
Okay. So this correct answer. And now you want VE. That means right here.
Point 89 millivolts.
What voltage you get? VE. That means from admitter to the route. They say VBB minus 0.7.
2.89.
2.89. Who else? Okay. 2.89 is correct. And IE, you get IE. Okay, VE, you divide RE. Okay, so we already given you the formula here. I hope you know how to do calculation. Okay, then we don't have to spend time. Okay, to try to get through it. Okay, VC, VCC minus VRC. Only thing is, if you get a question or anything, let me know. We can help. However, very soon or later, you don't have that formula. You have to memorize, understand it in order to do very basic calculation. You know, you apply for the job. They can give you this circuitry. They can asking you, how do we get VBB? You don't have to calculation, but you have to telling you how. The answer will be can using the voltage divider law. Okay? Or they say, if I want to get the meter voltage, how? Then you have to say, you take the VBB minus 0.7 volt, then you get the VE. Okay? After you get a VE, they can ask, okay, now we want to know the current IE. And you say, okay, you get a VE, you get IE. That's why you can get the IE. The thing is they only make sure you get a basic understanding. They not try do calculation. Okay?
One question.
Yeah.
I think I saw on your slides earlier about this VBB and how we are using the voltage divider here. And it says we can assume that it's a voltage divider, meaning the base current is much smaller than I1 and I2, so they're approximately equal. But what if it's not? So what do you do in that case? It's talking about something, go back and do it differently. Can you give us some advice regarding that?
No, the thing is we not emphasize on, designer. Okay? So that's why we only using the more application, more way they use it. If you can see, you can go through this circuitry, okay, and you go to amplify, you go to operation amplify, you go to anywhere they on the time using voltage divider. Only thing is to me, let's say money. We cannot like working on the left volt. Okay, they're using the voltage divider. Most of them. The thing is, if you're doing by yourself, you don't want to using the true power supply. That will be asking for more money. Even they can get almost the same answer. So, any question on this circuitry? Okay, now this one, PNP. Okay. Now, they want calculate VBB. Everyone already know. VBB here. Take 10 volt times R1 divide R1 plus R2. This is the formula they given to you here. And now they want to calculate the VE. Okay. If I given you the meter, I want to measure VE. How to make a connection? High side of the meter and a low side of the meter. How do we connect it?
If you put it like that, VE, just VE, the low side has to be on the ground.
Perfect.
That's one.
Yeah.
And then the high side wherever
Yeah.
you want, which would be the emitter, where your E letter is right there.
Right. You very good one. You know everything. That's what we want.
Not every.
Right. Okay. What I want you guys the same like this man. Okay. That means you can understand. You can do the technician job, no problem. However, if you still want keep moving, guarantee someday you will be engineering, no problem. Okay. You get through this program, you much better than any student like at you. Why? The thing is they don't know much about equipment, don't know much about how to working with the circuitry using scope or meter or anything. In here, you get everything for you. You working on. Okay. And if they want VE, they already given you formula here. Okay. And IE. I guarantee you will be get the assignment to working on this circuitry. So we already given you the formula. If you confused or anything, let me know. Okay, we'll help you out. Okay, if VE, high side DMM connect to ammeter, low side connect to the ground. However, for calculation, you understand at the ammeter here, you get 0.7. You add 0.7 volt to VB. That means to the ground. That's what you get VE. Okay. And if you want the current IE here, okay, you get the VCEE and you get VE. You get the current IE equals VEE minus VE divide RE. That's Ohm's law. Okay. And if you run IB or IC using the formula, same thing for NPN. Okay. And VC mean here. VC mean from collector to the ground. So that they will be IC times RC. Okay. And that one, VEC, you take VE minus VC. Yeah, you will get assignment, okay, to working on NPN, and that one will be PNP. And also, you will be get assignment for MSIM simulation. Okay. By the way, next week I will be teaching for few students in Tech 2 on room 240 about B-Spy simulation. Whoever once you learning on PSPI simulation, okay, then your guy can be at 5 o'clock on Monday. The thing is you get a true simulation, MSIM simulation, PSPI simulation. You can see the difference. PSPI simulation, more theory, okay, and MSIM 7 simulation, that hand-on training for really working, okay, in electronic. You have to using scope, you have to using the meter, you measure voltage, you measure current. How can you do? That is the difference. And now in K, PNP, they get negative power supply. That is on the formula. You will be need that to do a calculation. Okay? Like VBB, same thing, voltage divider. If you want VE right here, VE equal VBB adding 0.7. Okay? IE, that means the current through admitter, they will be equal 0 minus VE divided RE. Okay? So basically this formula, very simple. Okay? More time you're working on, that's why you can memorize it. Okay? And Darlington connection. You understand a Q1 they get a amplify with beta 1. And a Q2 get the beta 2. That only telling you one thing. If you want to get a more current, you're using the Darlington. Okay? Circuit. I given you example. You get beta 100, beta 200. So 100 times 100, so the gain will be very big. However, whenever you're working with the circuitry Darlington here, make sure you have to be very careful. Any touch is the wrong one, wrong way, can cook the circuitry right away. The thing is, the current is too high. Okay, so basically that's just for the DC. Okay, and any question only on the DC? I want you, when you're looking into the transistor, you know NPN or PNP. You know how the current flowing. Okay, and basically transistor by NPN, PNP can be either they can be working in saturation in the cutoff. If you're using like the switch, you turn on, turn off the light. You see that? And the transistor using to control, they must be in cutoff and saturation. Okay. However, if you want to design the amplifier to make your voice louder and louder, then they have to be in active region. Okay, so basically the transistor can be using, okay? Either like switching or amplifier. Okay, and the calculation, if we really try, make sure you understand a voltage divider law. Okay, that's what we try to get you guys working on either simulation and calculation. Okay, any question, anything? Okay, if it's not, okay, I want to bring it up, that thing for you. Okay, now, this basically in the level. Okay, now, let's see. You know that will be a common emitter amplifier. That means next week you will be learning about transistor amplifier. So if you're doing this lab, okay, my question is, when you run, okay, it fail and you need help, okay, then first thing is you cannot say, show them instructor fail and he looking into that side to help you. However, you have to first thing asking lab instructor, this is the lab you're working on. Okay. However, you can see this is they telling you what's going on. Connect generator. Okay. You can see the difference. In the lab you run, they're not telling you how to make a connection. So that's why normally the question, good one will be, can you looking into the circuitry telling me the correction right or wrong? I given you example. Generator connect here. And this not connect, you must connect. You see that? And also, this not connect, then if you need C2, you have to connect. Okay? That means at least the connection have to be right. And today, I just bring up one thing. When they say they want to apply sideways, you have to get sideways from generator. Okay? 300 millivolt peak to peak. How can you get that small voltage?
That's that offset thing that you guys talked about, right? Like pulling out the knob.
Exactly. You very good one. Uh-huh. That means the generator. Okay? You see that? The knot here, right? Put it out. Okay. Normally, they not put it out. You all go up, going down to minimum, they get around 1 volt. They cannot go to 300 millivolt. Okay? So you want a small voltage, put it back, put it up. Okay. Now, another one. I also to asking you. Now they say on this circuitry they wanted 300 millivolt. So 300 or 200 millivolt is too small. Even you put it out the offset, they cannot going down to that point. What can you do?
There is that attenuator also.
Perfect. You can see right here, attenuator. Okay? That means you connect the generator output to in here. Okay? And the out here now will be connected to here. Okay? The thing is that will be a attenuation. they will be given you up to 20 millivolt peak to peak, 40, 30 millivolt peak to peak. Okay, you must be using a attenuator. Okay, that will be help. If you know how to make the connection right, and you know how to apply the right voltage frequency, then that the job will be very, very easy. Okay. Next week we'll be going with the common base, common emitter, common collector, amplifier. Okay. So up to this point, do you have any question, anything? Okay. The thing is, you can take easy. I don't care. However, everything you know how to do, what to do. Okay. That be fine. And anything you get a problem, you cannot do it or you cannot understand. Okay. Ask the instructor. If you want to ask me, you can text for me. I can on Zoom with you to talking about one thing you cannot get through it. Okay. Basically, we do whatever you help your guy. Okay. Can do your job. Okay. Any more questions? Okay. If it's not, then we will be stopped. Okay. And we'll see you on Monday.
Thank you.
Okay.
Thank you.
Yes, sir.
Okay.
you.
Night, everyone.
Good night, sir.
Right.
Bye bye.